So we were talking about fundamental domains. And there's a picture that I wanted to make very concrete that we have been playing with. And maybe I want to draw it a little bit differently today. So let me draw it like this, like this. Okay. So again, you should think that this is the representation of the symmetric group S3 by reflections. And we're going to think that this is this fundamental chamber that we were talking about last time. Okay. So I think I called it D. This is D right here. And then this was the reflection S1. And this is the reflection S2. Okay. And one thing that I was in the middle of so D, remember, is this closed cone. So it includes the faces. Okay. And I was in the middle of proving a proposition for you, which says that any vector in this vector space can be achieved uniquely from exactly one of the points in D by letting the group act on it. In other words, this is the proposition that every point in my vector space is a group element acting on something in the fundamental domain. So for some group element and some vector in the fundamental domain. And this mu is unique. Okay. And so last time I proved the first half of this proposition, that we can always do this, but I haven't proved uniqueness for you. Okay. And so that's what I want to prove today. So existence we did already. And now I want to prove uniqueness. And of course, what that amounts to is basically proving that you cannot take one point in D and send it to a different point in D by the group. Of course, this is equivalent because if you had a point that can be written as W times mu and U times nu, if you had lambda equals W times mu equals U times nu for mu and nu in the fundamental domain, then you would get an expression for mu as something in terms of nu. Okay? And so what I'm going to do is prove that if you have something like this, if you have 2 points in the fundamental domain, which are related by a group element, then they must be the same element. They must be the same vector. So suppose that, let's say that W lambda is equal to mu for lambda and mu in the fundamental domain. And what I want to prove is that actually lambda is equal to mu. Okay? And I think you've seen by now that the way that I prove a lot of these things is by inducting on the length. And that's what I'm going to do here. I'm going to induct on the length of W. Now, of course, if the length of W is 0, which is the initial case, then there's nothing to prove, right? Because then W is the identity. And then the identity times lambda is mu, so lambda is equal to mu. So there's no problem there. And now the usual things. We suppose that it's true for lengths less than the length of some w, and now let's prove it for w. And then again, we're going to do the usual argument where we want to apply the proposition for a smaller w. And so the way we do achieve that is by taking a reflection that makes w shorter. So let's take a generator S which makes w shorter. And of course, what that's going to mean is that there's a corresponding positive root. Actually, it's not just a positive root. It's one of the simple roots, right? This is a generator, and so there's a simple root corresponding to it. Yeah. Remember that delta is the set of simple roots. And we know we have this dictionary that says that we can write this combinatorial property in terms of the geometry of the group action by saying that W acts on this alpha, which is positive, by sending it to a negative root. Okay? So what am I going to do now? I'm going to make the following computation. Alpha is positive, and lambda is in the fundamental domain, right? And so, by definition, the fundamental domain, maybe I should write this out explicitly, just to remind you. The fundamental domain consists of my vectors lambda, which have non-negative inner product for all the positive roots. Okay. So since alpha is positive over there and lambda is in D, that means that this inner product is positive, or non-negative. Right? Lambda. Okay. Now somehow I have to incorporate this, and here we can use this nice property of this inner product, that the way that the group acts on this vector space, it doesn't affect the inner product. So if I let W act on alpha and on lambda, I'm going to get the same inner product. So this is a lemma that we proved, or actually that I told you guys to prove. And then what I get here is W alpha, and then W lambda is mu. Right? But now if you look at what I have here, I know that W alpha is a negative root. Right? And I know that mu is also in my fundamental domain. Okay? And so I know that if I take something in my fundamental domain, and I take the inner product with a negative root, I'm going to get something negative. So I get less than or equal to 0 here. Okay. And so, well, this might not be very exciting that I just proved that 0 is less than or equal to 0. Well, that part is not exciting, but what's exciting is what I squeeze in the middle, right? Because if this is 0 and this is 0, then all of these things in the middle have to be 0. Okay. So what I just proved is that the inner product of alpha and lambda is 0. Okay. Now the good thing about this is that alpha is the root that corresponds to S, right? And so now if I look at how S acts on lambda, well, S is one of the generators, and so it just acts as a reflection, and we know the formula for that. Lambda minus 2 times the inner product of alpha comma lambda alpha. Okay. But this is 0, and so what I proved is that S lambda is equal to lambda. Okay. And then I think I'm done, because I have that mu is equal to W lambda, but lambda is equal to S lambda. So this is WS lambda. And so now what I have proved is that mu is equal to a group element times lambda, where this is a group element is shorter than the previous one. Okay. This has length less than the length of W. So by the induction hypothesis, mu and lambda must be equal to each other. So by induction hypothesis, lambda is equal to mu. So that proves my proposition. Any questions about this uniqueness proof? Okay. Now, let me point out something that is very important here in this proposition, which is that, I want to understand the situation of how this can happen when lambda can be equal to W times mu for a mu in the fundamental domain. And I just proved that this can always be done and that mu is unique. But what I'm not at all claiming is that W is unique. Okay. And so maybe what we should understand now is basically, when I have an equation like this, what can W be? Because W is not unique. And so let me just say explicitly, because actually we basically already proved this. Let me understand, how can it be that we know that if lambda and, I think this doesn't show up on the camera so high. If lambda and mu are in the fundamental domain, and W lambda is equal to mu, then, well, I just proved that lambda is equal to mu, okay? But now I also want to say what W must be. And in fact, maybe I would like to look at the picture here and illustrate to you the kind of thing that can happen. Lambda could be on this brown ray, right? And now the question is, how can I let the group act on lambda and still land at lambda? Land at lambda. Yeah. So what group elements send this point here to itself? Just S2 and nothing else. Okay. And basically what I want to prove in general is that this is the only thing that can happen. That if some group element sends lambda to itself, then it's just a situation like this. More precisely, W is a product of reflections, of simple reflections that fix lambda. Okay. So the point is this. The point is that, if you look at a point here, then obviously S2 is going to leave it fixed. And what this statement says is that this is the only way that this can happen. If a group element fixes lambda, then it's obvious. Okay? It's not like S1, S2, S1 is going to fix lambda. So why is this? Well, basically, let's look at this proof again more carefully, and we'll see that I already proved this. Okay? So let's look at this proof and prove this stronger statement. So we have W lambda is equal to mu, and we want to argue by induction that lambda is equal to mu, and W is a product of reflections that fix lambda. Okay? So I assume this. I do it by induction, so for length 0, it's obvious. Now, I assume that it's true for WS, and I prove it for W. Okay. What did I just show? I showed that if W lambda is equal to mu, then WS lambda is equal to mu. This guy is shorter. And this guy is shorter, which means that by induction hypothesis, WS is a product of reflections such that each reflection fixes lambda. And S also fixes lambda. So W is equal to WS, which is a product of reflections that fix lambda, times S, which also fixes lambda. And so basically this is proved already. So let's continue on this topic now and prove another proposition. This corollary right here explains to me if I have a point in my fundamental domain, what are the group elements that leave it alone? Okay. But this is only for the fundamental domain. And I want to prove it for the whole thing. So for any point in V, I want to understand exactly what are the group elements that leave it alone. Okay. So what I want to prove is if I have some element of V anywhere in V, not just in the fundamental domain, then the subgroup of W that fixes lambda is generated by the reflections that fix lambda. Okay. So what am I saying here? I'm saying that, for example, if you look at some point right here, say this is lambda, and you want to know which group elements fix lambda, then all you have to do is look and see which hyperplanes go through lambda, and those hyperplanes reflection across them fixes lambda, and nothing else does. Okay. So for example, here we know that there's another hyperplane that I haven't drawn here, and reflection across that hyperplane is the only thing that is going to fix this lambda. So this proposition is saying. Okay. And then the same result is true if I do it not just for a single point, but for a set of points. So the same is true for any set of points. So again, if now I give you some set like this, and I tell you this is U, and I ask you what group elements fix U, all you have to do is see which hyperplanes contain U. And those reflections generate everything that fixes U. Okay, so proof, well, basically, I already proved this for lambda in D, right? That's what that statement says for lambda in D. And so now I want to extend it. So for other lambdas, basically, I mean, you can imagine that I have a statement that is true for things that are in D. Now, here I have a statement about points that are in V, and I would like to reduce it to that statement. And the way to do that is that if I already prove something for the fundamental domain, I know that I can send this point to my fundamental domain. And so that's what I'm going to do. So let me write lambda as W times mu, where W is a group element and mu is in the fundamental domain. Okay. Now, let's suppose that some group element U fixes lambda. Okay. U lambda is equal to lambda. Now, of course, what I want to do is translate this into a statement about mu, because I know that this proposition is true for mu. Okay. So I rewrite this as U times W times mu equals W mu. Okay. And then I let W inverse act on the left of this. And I get the W inverse U W of mu is equal to mu. Okay? And you see what I have now is a group element which fixes mu. And mu is in the fundamental domain, so I can apply my corollary, which says that W inverse UW is equal to a product of reflections, S1 up to Sk, all of which fix mu. Okay. Now, what I'm trying to do then is I started with a statement about lambda, I translated it to mu, I used the result for mu, and now I want to translate back to lambda. And so what I want to do is write U as a product of things. So I solve for U here. So U I get is equal to, I multiply by W on the left. And W inverse on the right. And I get this. Okay. And now I want to write this as a product of reflections that fix lambda. Now, what are reflections? Reflections are the conjugates of the SIs. Okay. So then the natural thing to do here is to rewrite this product W S1 S2 SK W inverse as W S1 W inverse times W S2 W inverse times W SK W inverse, where all of these are reflections. Reflections. And if we have any faith in this line of proof, then it shouldn't be hard to check that these reflections fix lambda. So I need these reflections to fix lambda. And then the way that I do this computation is basically, I know that lambda is W mu, right? So this is W SI W inverse W mu. Then W inverse and W cancel each other. So I get W SI mu. But I know that SI leaves mu fixed. So this is equal to W mu, which is lambda. And then I get this result. And so that proves this first one. Now, if you want to prove the second one, maybe I'll just say something about it. So this is A, and this is B. So I proved A. Now what about B? Well, the thing is, let's say, for example, that we go here. So this is my set U, and I want to know what elements of W fix this set U. Now the thing is, you can imagine that if an element of W sends all of U to itself, then probably it's going to send maybe this also to itself and anything along this line to itself. How can I justify that? Well, the thing is that every element of W acts as a linear operation. And if a linear operation fixes this segment, then by linearity it's going to fix everything. It can't send this somewhere and then this somewhere else because it has to send a line to a line if it's linear. Okay? So W fixes U if and only if W fixes the whole span of U. By linearity of how W acts. Okay. So if I have an element that fixes U, well, it has to fix this whole line. And that's taking it in one direction. Okay. But now I can take it in the opposite direction and say, well, if I want to prove that W fixes a linear space, then it's sufficient to prove that it fixes a basis for that linear space by the same reason. In other words, in this case, if I want to prove that this whole line is fixed, then it's enough to prove that one of the points on it is fixed. And if I prove that this point is fixed, then by linearity, the whole line will be fixed. Okay? And so this is equivalent to saying that W fixes a basis for this thing. So W fixes lambda 1 up to lambda k. For some basis lambda 1 lambda k of the span of U. Okay. And the reason in doing this is that this seems to be kind of an infinite statement, but I have translated it into a finite statement. Okay. And once I have this finite statement, I can just do it by induction. I basically did the case k equals 1, and then a simple induction shows that you can extend this for the rest. So these are basically a couple of technical lemmas that I needed to prove, so that now we can understand this picture in an even better way. And that's what I'm going to do for the rest of the class, is draw some pictures and justify that these pictures are telling us the full story. So what is this picture that I keep drawing? Now, not just this, but the whole picture that I drew last time. Well, what I want to do is this. For each positive root, I know that I have a reflection. Okay? A reflection across some hyperplane. And so let me consider all those hyperplanes. So those form what is known as a hyperplane arrangement. This is not a technical word, it just means an arrangement of hyperplanes. Yeah? Hyperplane arrangement consisting of, for each simple root, I have a hyperplane. Okay. I'm going to draw a black and white version and a colored version. Okay, so in the black and white version, these things just look like these are the hyperplanes, right? This is S1. S2, and this is S, and they correspond to the simple roots alpha 1, alpha 2, and then the positive root alpha. Okay. So there's something you should notice about hyperplane arrangements in real space. I think I mentioned this last time. If you're living in real space and you take a hyperplane. Yeah? So that hyperplane is given by an equation, let's say x plus y plus 2z equals 0. Now, if you imagine taking your space and taking out that hyperplane, then you have divided the space into two sides. The side where x plus 2 y plus z is positive, and the side where it's negative. Yeah? So when you take a real vector space and you take out a hyperplane, you have now separated the space into two pieces. Now, it's very important that you notice this is for reals. Yeah? If you did this over the complex, you take an equation, something is equal to 0, but the complex numbers are not ordered. Because they're not ordered, you can't say there's a positive side and a negative side, because there's no such thing as positive and negative complex numbers. So this is a specific phenomena for reals or for fields with an ordering. Okay? But so far we've talked about the reals. So now imagine if I take all of these hyperplanes and I take them all out. And so now what I'm left with is, in this case, 6 pieces that are separate from each other. Okay. And so the hyperplane arrangement divides my vector space V into what are called as chambers. And a chamber is just what I'm telling you, it's one of the connected components that you get when you take your hyperplane, you take your vector space and you get rid of these hyperplanes. Okay. So in this case, here are my 6 chambers. Okay. Now there's one chamber that we understand quite well by now, which is, well, D is the fundamental domain. It includes the borders. But now remember that initially I defined C to be to be this chamber without the borders. Okay. So there's one special chamber called the fundamental chamber. And we've seen that it has walls basically h alpha 1 up to h alpha n, where these alpha i's are the simple roots. Okay. So in this example, my fundamental chamber is C, and it has two walls, one corresponding to the simple root alpha 1, and the other one corresponding to the simple root alpha 2. Okay? And I want to actually get these colors to match, so let me color this blue, and let me color this brown. And then here's alpha. Now, what do I want to say? Well, it follows from what we proved now that any point that is not in the fundamental chamber can be sent to the fundamental chamber by a group element. Okay? And so now if you look at this, basically, the other chambers are all obtained from C by some group element. So the other chambers are basically the things that you obtain from C by letting a group element act on it. Okay. In particular, the number of chambers that you have is exactly the number of elements in the group. Okay. And so I'll add colors to this in a second because I'll need to. But for now, I want to say that we've done this already. So if you let S2 act on this chamber, then you're going to send it over here. So this is S2 times the fundamental chamber. If you let S1 act on it, then you get S1 times the fundamental chamber. Now, for example, if you let S2 act on this one, then it's going to land you over here. S2, S1, C. If you let S1 act on this one, you're going to get S1, S2, C. And finally, if you let S2 act on this, or if you let S1 act on this, you're going to get S2, S1, S2, C. Okay. Now this picture is not surprising to you because I drew it the first day of class, but now we finally proved that this picture actually makes sense. Okay. And this is really what it means. Each region corresponds to a group element. Okay? Yeah?
So the fundamental chamber includes its boundary?
No. So the chambers are open, and they're basically the things that you obtain when you take out the hyperplanes.
But the fundamental chamber also doesn't include its...
That's right. So because remember, so there's difference between fundamental chamber and fundamental domain. So the fundamental chamber is C, and it's open. And the fundamental domain is D, and that's what I get when I close it and I include the
So there's a reason you called it C, because of the previous section.
Yeah.
I see.
Yeah, so I had a D. That might be why you're confused, because I had a D, and initially I drew it as if it contained it, and then all of a sudden I just erased the letter D and put C, and I said, no, it doesn't contain. Now, what I want to do is, I mean, I have perfectly natural labels for the chambers, but I actually want labels for everything in this picture. And for example, what should I call? Let me just switch. Instead of S1 and S2, which are the names of the reflections, let me give them the names C1 and C2, where C1 is going to be this blue piece and C2 is going to be this brown piece, and that's why I want colors here. So I'll define this concretely in a second, but here's C1, and here is C2. So what exactly are C1 and C2? Now they're geometric things. So the thing is, if you remember the way that I defined C, this is the set of points which have inner product with all the simple roots negative. Sorry, positive. Okay. But now I want to define C sub I for each subset of the simple roots to be the set of points such that. So I you should be thinking of as basically a sum of these roots. Okay. And so I want to define this to be basically, well, let me get rid of this I. I don't need this I. So here your inner product with all the simple roots is positive, and here I'm just going to say some of them are positive and some of them are 0. So there's 0 for exactly these roots, and positive for the other roots. So let's go to this picture and make sure that this matches up. C1 is supposed to be the set of points in my vector space such that their product with alpha 1 is 0 and with alpha 2 is positive. Okay. So if your product with alpha 1 is 0, that means you're on this line. And if your product with alpha 2 is positive, that means that you're on this side of the hyperplane. And so really what I get is this little piece. That's C1. Another way of thinking about it is that I take some of these strict inequalities and make them now equalities. And so I'm just saying go to some of the walls of C. For example, this is C2. Now let me ask you, is this point included in C1 or in C2? It's actually not in both. And the reason is that I made this a strict inequality. So it's in the closure of both, but C1 doesn't contain this little point, C2 doesn't contain this little point. This little point has its own name. So what should I call it? Well, it's basically the only point that is perpendicular to alpha 1, perpendicular to alpha 2. So this deserves the name C12. Okay. And so that's how I label the faces of C. C is some cone, and now as I go to the faces, I just end up adding subindices. Okay. So now what should I label the other things in my picture? For example, what should I label this ray right here? I think there's a natural name for it, because again, remember that this reflection is the reflection S2, and this reflection is the reflection S1. So if I want to give this guy a name, I don't have to give it its own name, because the thing is that I know that everything in this whole picture can be obtained from something in the fundamental domain. Fundamental domain now includes C, C1, C2, and C12. Okay? So what is this an image of? Well, it's basically what you get when you take C1 and you flip it over by acting with S2 on it. Okay? I hope one of these blue things works. Well, you can pretend this is blue. I want to call this, let's just turn to purple. So this was C1. Now this is going to be what I obtain when I apply S2 to C1. And let me continue doing this. For example, this ray is the one I obtain from C2 by reflecting across S1. And so let me give it this color and call it S, where did I say? S1 of C2. What about this one? This one is what you get when you, for example, take this thing and reflect it across here. Remember, this is the reflection S1, S2, S1. Wait, am I saying that correctly? No. This is easier. This guy is just the reflection of this guy across S2. Right? So if I apply S2 to this thing, I land here. And so this guy should be brown also. And I should call it S2, S1, C2. And then this guy is obtained from this guy by reflecting across S1. And so it deserves the name S1, S2, C1. Now let me ask you something. What do I want to ask you? Are these names ambiguous? Is there a unique name that I can give to these things? For example, is there another name that you could have give to C2? I'm anticipating that there is another name. S2C2, right? If you take C2 and you apply S2 to it, then you leave it alone. Or for example, this guy can also be called, I think, S1. I think this is S2, S1, C1. One easy way of seeing that is that C1 is S1, C1, etc. But, and so we see that the names might be a little ambiguous, but are the colors ambiguous? The colors are not ambiguous, and why are they not ambiguous? The reason they're not ambiguous is because I proved a theorem that tells me that I cannot send any point in my fundamental domain to a different point in the fundamental domain. So a brown point is never going to land on a purple point by the group action. Okay? Question?
One thing that's kind of troubling is the labeling of C12 as its own little thing we're saying. And you said it's perpendicular to both alpha 1 and alpha 2. So I'm thinking
just because it's the zero vector, so that's perpendicular to everything.
Yeah, right. Okay.
And then this guy, again, you could give it a lot of names like S1, C1, C2. I mean, any group element leaves this guy alone. And actually, I'd rather not give it the color green. I might just think that this has both colors, purple and brown. Okay. But now let's say a couple more things about this picture that are very nice. For example, what is the length of a word? What is the length of a group element? According to this picture. So how do I find a group element in this picture? A group element is a chamber, like this one. What's the length? Well, it's basically, I'll leave it to you as an exercise to prove, that it's the number of hyperplanes that is separating that region from your home region. So, exercise. The length of W can be understood in this picture as the number of hyperplanes you need to cross to get from your home region to the region labeled by W. And here you see it. You need to cross one hyperplane to get to the simple reflections. You need to cross two hyperplanes to get to the things of length 2. And you need to cross 3 hyperplanes to get to the thing of length 3. And so that's a very nice way to understand what the length is geometrically. Now, what about reduced words? How can I understand the reduced words in this picture? For example, how can I understand that a reduced word for this group element is S2, S1? Well, there's a very nice way to do it, which is to carry out this walk and keep track of the colors that you're crossing. Yeah? So I cross brown color, which is S2, purple color, which is S1. And that's a word, S2, S1. For example, for this guy, what are the possible walks from my home to here? There's 2. I either go this way or this way. So I go either brown, purple, brown, which is S2, S1, S2, or purple, brown, purple, which is S1, S2, S1. So the reduced words for W are the colors, the sequences of colors of hyperplanes that I cross in a minimum, in a shortest walk from C to WC. And I think this is very good news for those of you that are fond of geometry more than you are fond of combinatorics, because now whenever you're thinking of a sequence of SIs, which maybe you're tired of thinking about, well, you can just think, I'm just walking in this picture. Yeah? And a word is just a walk in this picture. It's a nice way to understand it. Okay. All right. We'll continue next time.
Some sort of a model with framework to do something like this in 3 dimensions.
So actually, Mike made a model like this for the homework.
You can point inside it and then go, aha.
Yeah.
That would be nice.
I thought I would bring it, but it's a little delicate.
Yeah, that's the problem on things like that. And for demonstrations, you need one that's about this big, so that you can see it from the back. Otherwise, you're standing in front of it, you can't show it.
If you have 2 things less than hot water, and they're both